I mean, just imagine pulling down a decade-old Python project and having it compile and run flawlessly on the very first try.
Yeah, that sounds like actual science fiction for most of us.
Right. Like no hunting for the right virtual environment, no fighting with, a broken requirements.txt file.
Or getting those completely mysterious C extension compilation errors just because your system's GCC version is, like, slightly off.
Oh, I hate those.
Yeah.
But, well, the crazy thing is, in the Rust ecosystem, that kind of stability isn't a miracle. It's literally just a Tuesday.
It really is. And for a senior backend engineer, coming from Java or Python, that realization is pretty profound.
Yeah, because you've spent years building up this muscle memory, right?
Yeah.
You already know how to build scalable systems.
Exactly. So the thought of starting over, of fighting a brand new ecosystem just to figure out, like, how to format a string or install a package, it's just exhausting. It's that massive friction of the unknown.
And that is exactly why today's deep dive is going to be, honestly, so deeply satisfying for you. Because we are tackling Chapter 2 of Rust for Backend Engineers.
Which is where things get real.
Very real. Up until now, you understood the why of Rust. We covered all that in Chapter 1, right? The promise of memory safety without a garbage collector, the performance trade-offs, and exactly where Rust sits in the landscape compared to Python and Java.
Right. The theoretical foundation.
Exactly. But today, we are moving from theory into actual practice. We're setting up the development environment, mastering the foundational tools, and this is the big one, confronting that notoriously steep learning curve with a modern AI workflow.
I think, though, we really need to set a reassuring tone right out of the gate here.
Fair enough. It can be intimidating.
It can. Yes, Rust introduces entirely new paradigms. But what you are going to discover today is that its world-class tooling is fundamentally designed to, well, catch you when you fall.
It's a completely different architectural philosophy, right? Compared to the days of just piecing together some fragmented toolchain from scratch.
Precisely.
Okay, let me stop you there and unpack exactly what that means. Because before you can write a single line of Rust, you need the tools. And the source material points out that Rust's out-of-the-box experience feels like just a massive upgrade.
Oh, a huge upgrade.
It starts with literally one single terminal command on Mac or Linux to install something called Rustup. But, I mean, what is Rustup actually doing under the hood?
So think of Rustup as your master toolchain manager. It's not just like a simple downloader script.
Okay.
It handles getting the compiler, the standard library, and all the associated tools onto your system. But it also manages different versions of Rust and even different target architectures.
Wait, like cross-compiling?
Yeah, exactly. If you're on a Mac but you need to compile a binary that will run on a Linux server, Rustup pulls down the necessary components to cross-compile with just a single command.
Oh, wow. That's incredibly handy.
It really is. And once that initial installation finishes, you essentially have three main executables. The first is Rustup itself. The second is Rustup, which is the actual core Rust compiler.
But, and the text notes this, you will rarely, if ever, invoke Rustup directly, which, coming from a Javac background feels totally counterintuitive. Why wouldn't I call the compiler?
Well, because calling the compiler directly means you have to manually pass it every single file, every library path, and like every optimization flag.
Right, which sounds like a nightmare.
It's incredibly tedious and error-prone. And that brings us to the third tool, which is honestly the absolute crown jewel of the Rust language. It's the reason you don't call Rustup directly. And that tool is Cargo.
Cargo. I have to admit, as a Python developer, reading about Cargo made me a little jealous.
I hear that a lot, actually.
I mean, in the PyCon world, my ecosystem is completely fragmented. I've got pip for packages, but then I probably need a virtual environment, so I'm using Venv or Conda, Poetry, Pipe-Invent.
The list goes on.
Right. Then I need setup tools. I'm using PyTest for testing. I need Black for formatting, Flake8 or MyPy for linting. Setting up a new project is like a major architectural decision before I've even written a single line of logic. It is just a Frankenstein's monster of configuration files.
And that right there is exactly why Cargo exists. The creators of Rust looked at that historical fragmentation in C++, Java, and Python, and they realized that ecosystem fatigue is a massive barrier to entry.
Yeah, it definitely is.
So they decided that tooling couldn't just be an afterthought. It had to be built into the language from day one. Cargo is your build system, your package manager, your test runner, and your project scaffolder, all unified into one single executable that literally ships with the language.
So practically speaking, if I want to start a new backend service, I don't spend an hour setting up boilerplate. I just type what cargo new and my project name.
Exactly. You type cargo new, and instantly it generates a standardized directory structure.
Just like that.
It's just like that. You get a cargo.toml manifest file dash, which is your single source of truth, sort of comparable to your pyproject.toml in Python or a pom.xml in Maven.
Okay, makes sense.
You also get an src directory containing a main.rs file with a pre-written hello world program, and it even initializes a Git repository for you automatically. You are ready to start coding in literal milliseconds.
That's awesome. And building it is just as unified, right? You just run cargo build.
Yep.
And if you want to build and execute the binary in one step, it's cargo run. Want to run your unit tests, just type cargo test. But, and I noticed this in the sources, they emphasize a specific flag for production. Cargo build release. What is the mechanical difference there?
That's a crucial distinction. The default cargo build produces a debug build. It includes all your debug symbols and skips heavy optimization so that it compiles as fast as possible for, local iteration.
Right, because you want fast feedback when you're coding.
Exactly. But when you append the release flag, Cargo tells the compiler to turn on all the LLVM optimizations.
LLVM being the back-end compiler infrastructure Rust uses.
Right. And it performs aggressive inlining, vectorization, dead code elimination, all the heavy lifting. It takes significantly longer to compile, but it ruthlessly optimizes your code. That resulting binary is what gives Rust its reputation for that C-like bare metal speed.
Okay, but here's where I need to push back a bit.
Go for it.
In Python, my iteration loop is incredibly fast. I change a line of code, I hit save, and I immediately run the script. Compiling a backend constantly, especially if Rust has a reputation for being this strict, complex compiler, sounds like trying to run through molasses.
Yeah.
Does Cargo build bottleneck my flow as a developer?
That is a very, very valid anxiety for anyone coming from an interpreted language. You're used to that instant gratification.
Exactly. I don't want to wait 30 seconds to see if I made a typo.
But Rust anticipated this iteration bottleneck. So to answer your question, no, it doesn't slow you down because you actually shouldn't be running cargo build every time you change a line of code.
Wait, I shouldn't?
No. Instead, you use a command called cargo check.
Cargo check. Okay, how does that solve the speed problem?
Well, think about what a compiler actually does. It has two main phases. First, it analyzes your code to make sure it's semantically correct. In Rust, this means it runs the type checker and the famous borrow checker.
Right, the borrow checker.
Yeah, as a quick primer, that's Rust's strict internal auditor that ensures memory safety without needing a garbage collector. Now, if you pass that audit, the compiler moves to the second phase, generating the actual machine code binary.
Okay, I fell.
Cargo check runs the entire first phase, but it completely skips the second phase.
Oh, I see. So it's like checking the blueprints for structural integrity without actually spending the time to pour the concrete and build a house. I'm just asking the compiler, did I break any laws, without asking it to actually print the law book.
That is a brilliant analogy. Precisely. It verifies that your code would compile, and it does it incredibly fast. As a Rust developer, you will run cargo check constantly.
That's a huge relief.
Yeah, and in fact, most modern IDE extensions like Rust Analyzer are just running cargo check in the background every single time you hit save. It gives you the immediate, real-time feedback you are used to in Python without the compile time penalty.
That makes a lot of sense. So Cargo handles the project life cycle, but it also handles code quality, right? Because the sources mention two other commands that basically replace my entire Python linting stack. First is Cargo FMT.
Right. Cargo FMT is the official standard formatter. It's exactly like Black for Python. It completely ends all debates about code style on your team.
Thank goodness.
You just run it, and your code is instantly reformatted to look like perfectly idiomatic Rust.
Love that. And the second one is Cargo Clippy. But from what I'm reading, Clippy isn't just a basic syntax linter like Flake 8. It sounds much deeper.
Yeah, calling Clippy linter almost does it a disservice. Clippy is an advanced static analysis tool. It doesn't just catch syntax errors. It catches common logical mistakes, performance bottlenecks, and non-idiomatic patterns.
So it's actively trying to make you a better Rust programmer.
Exactly. If you write a clunky Java-style while loop to iterate over an array, Clippy won't just tell you it's ugly. It will explicitly suggest rewriting it as a Rust iterator, and it will often provide the exact line of code to replace it with. Wow. It's truly like having an incredibly pedantic but brilliant senior Rust developer doing a code review on every single keystroke.
Okay, so we have this unified, powerful tool chain. Cargo's doing the heavy lifting locally. But, I mean, a fast compiler and a smart linter don't mean much if you can't easily connect your code to the outside world. Building a backend means relying on external frameworks, database drivers, serialization libraries. In Python, you're juggling pip and virtual environments just to avoid system-wide conflicts. How does Cargo handle external code?
Seamlessly. When you need a package, which the Rust ecosystem calls a crate, you just run cargo add followed by the crate name. Cargo automatically updates your cargo.toml file and fetches it.
And these crates are hosted centrally on crates.io, right? Which is Rust's equivalent to PyPI or Maven Central. But there's one specific detail from the sources regarding external crates that absolutely blew my mind.
Let me guess. Docs.rs.
Yes, docs.rs. When a crate is published, Rust automatically generates standardized documentation for it and hosts it at docs.rs. This is huge. In Python, I spend half my time hunting for a random read the docs page or, trying to figure out if a dead GitHub wiki matches the version I just installed.
Oh, it lowers the cognitive load tremendously. Every single library in the Rust ecosystem has the exact same documentation format, the exact same layout, and the exact same search functionality.
It sounds almost too good to be true.
And because the compiler generates the docs directly from the source code, they are always perfectly in sync with the published version.
Let's talk about those versions, actually, because managing dependency graphs is basically the bane of a backend engineer's existence. How does Cargo track these crates?
It relies on strict semantic versioning, or SEMVer. If your cargo.toml specifies a version like, say, 1.4, the default behavior is that Cargo will fetch the newest version that is backwards compatible with 1.4.
Okay.
That means it will pull down 1.4.0 or 1.4.5 or even 1.9.9, but it will intentionally never pull down version 2.0.0 because a major version bump implies breaking API changes.
Got it. And when you build the project for the first time, Cargo does all that complex dependency resolution, downloads the exact crates, compiles them, and then generates a Cargo.lock file.
Right.
Now, the rule of thumb in the text is, if you are building an executable application like a backend REST API, you commit that Cargo.lock file to version control. But if you are building a library that other people will use, you don't commit it. I actually have a question about that.
Sure.
Why wouldn't a library want deterministic build? Shouldn't everyone want exactly what they tested?
It's a great question, and it really comes down to overall ecosystem health. For an application, you absolutely want deterministic builds. You want the exact same subdependencies running in your production environment that you tested on your local laptop.
Right, obviously. No surprises in production.
Exactly. But libraries are building blocks. If every library hard-locked its dependencies, an application that uses 50 different libraries would end up with 50 conflicting locked versions of core packages.
Oh, right. That would be a nightmare.
By not committing the lock file, a library declares its flexible bounds, allowing the final application to resolve a single, shared version of a dependency across the whole graph.
That is incredibly elegant. But wait, talking about locking down versions and breaking changes gives me major anxiety.
Oh no, why?
If I'm locking down crate versions, what happens when the Rust language itself updates? I mean, I still have deep psychological scars from the Python 2 to Python 3 migration.
Oh, we all do.
It was an ecosystem-splitting disaster. Code broke, libraries fractured. It took a decade to resolve. Are we going to eventually hit, like, a Rust 2.0 that breaks the world?
This is exactly where Rust shows its architectural brilliance. The core team intentionally learned from the trauma of the Python 2 to Python 3 migration. They realized that breaking the ecosystem destroys trust. So to solve this, Rust introduced something called editions.
Editions, yeah. The text mentions 2015, 2018, 2021, and the current edition, 2024. What are they, functionally?
An edition is a coherent set of new features, syntax changes, or even new keywords released as a package every 3 years. But here is the critical, non-negotiable design decision. Editions are completely 100% backwards compatible at the compiler level. Code written for the very first Rust 2015 edition still compiles perfectly on today's compiler.
Wait, how is that mechanically possible if they introduce new syntax?
Yeah.
For example, the async keyword didn't exist in 2015. What if I used the word async as a variable name back in 2015, and then in the 2018 edition, it became a reserved keyword? Wouldn't the new compiler choke on my old code?
It would if it parsed them the exact same way. But think of editions like different local dialects of the same language.
Okay, I'm tracking.
The edition is specified per crate in the cargo.toml. When the Rust compiler reads a crate, it looks at that specific file, sees edition 2015, and parses it according to the 2015 dialect rules. So your old variable name remains perfectly valid.
Oh, that's clever.
But here's the magic. The compiler acts as a master translator. It takes that 2015 dialect, and it takes your brand new 2024 dialect, and it translates both of them down into a universal underlying Esperanto.
Ah, so the underlying compiler representation of the Esperanto hasn't fundamentally changed, even if the surface syntax has.
Exactly. Under the hood, they both compile down to the exact same high-level intermediate representation, or HIR. Because they share that core representation, a brand new backend service written in the 2024 edition can seamlessly pull in an older crate written in the 2018 edition. They link together perfectly in the same binary. There is no ecosystem split.
That is massive for enterprise adoption. You can confidently build a million-line code base knowing the foundation won't fracture out from under you in 3 years. Cargo prevents dependency hell, and additions prevent version migrations.
It's a very safe bet.
But, well, let's be real here for a second. We have to talk about the wall.
Ah, the wall.
Because the strictness of the compiler itself creates a massive barrier for newcomers. How do you survive the initial shock of the Rust compiler rejecting code that looks perfectly, obviously fine to a senior Java or Python engineer?
Yeah, we do have to give an honest assessment here. The learning curve for Rust is incredibly steep. It is likely steeper than any language you have encountered so far.
It's notoriously tough.
And that's because concepts like ownership, lifetimes, and trait bounds simply have no direct equivalent in Python or Java. The garbage collector completely hides memory management from you in those languages.
Right. And just to make sure we're grounded, let's briefly define those terms for the listener, since they won't fully dive into them until the next few chapters.
Good idea.
Ownership is Rust's system for deciding exactly which part of the code is responsible for cleaning up memory. Lifetimes are how the compiler guarantees a reference won't point to deleted garbage data. And trait bounds are essentially Rust's stricter, safer version of interfaces.
Perfect summary.
But the sources say that wrapping your head around this in the first 2 to 4 weeks is, well, brutal. You will write logic that you know is logically correct, and the compiler will just say no.
And this brings up a phenomenon I like to call the error message paradox. Rust has famously excellent compiler error messages. If the borrow checker rejects your code, it doesn't just vomit a cryptic stack trace onto the terminal.
Right, no Java null pointer exceptions here.
Exactly. It politely explains exactly what rule was violated, it points to the exact line of code, and it very often suggests the exact rewrite you need to apply.
But knowing how to fix an error doesn't mean you understand why you had to fix it. If you just blindly copy and paste the compiler's suggestion, you haven't actually internalized the underlying ownership rule that you violated. It's like passing a math test by looking at the answer key. You still don't know how to do the algebra.
Exactly. Understanding why the compiler is complaining requires a fundamental paradigm shift. And this is where the modern developer workflow becomes your absolute secret weapon.
Right, the Claude Code solution. As a senior engineer today, you are already using AI. But the text emphasizes that in Rust, an AI agent like Claude Code isn't just a luxury. It is your biggest advantage in conquering this specific learning curve. But it's about how you use it.
Yes, the how is critical.
Instead of just asking it to mechanically translate a Python script into Rust, you use it to translate the code idiomatically.
It acts as the ultimate bridge. When you hit that wall and you get a borrow checker error that you just don't understand, you don't just ask Claude to write the fix. You ask Claude to explain the underlying concept.
Give me an example.
Well, if you have a heavily object-oriented Python class you want to rewrite, Claude can show you the data-driven patterns that actual Rust developers use, rather than letting you force Python paradigms into Rust syntax, which the compiler will fight you on relentlessly.
This is where the workflow completely changes. You encounter a totally alien concept. Let's say you try to pass a list to 2 different functions. In Python, you just pass the reference, no big deal.
Very standard.
But in Rust, you accidentally move the list into the first function, and the compiler screams that the second function can't use it. Instead of spending 3 hours reading deeply theoretical documentation on move semantics, you ask Claude to explain it using analogies to the Java or Python concepts you already deeply understand.
It grounds the alien mechanics in your existing mental models. It explains that in Rust, by default, passing a variable transfers ownership entirely, unlike Python, where you are just passing a shared pointer.
So we have to be careful here, right? We aren't outsourcing our engineering to AI.
No, absolutely not. If you outsource the thinking, you will never actually learn Rust. You will eventually hit an architectural wall that the AI cannot seamlessly fix for you. What you are using Claude for is compressing the feedback loop.
It's like having that pedantic, brilliant senior developer we talked about earlier sitting right next to you as a pair programmer.
Exactly.
A practical workflow looks like this. You describe your architectural goal, Claude generates the initial Rust code, and then you read every single line. If there is a symbol, a lifetime annotation, or a keyword you don't fully grasp, you stop. You ask Claude to explain it. You spend 5 minutes clarifying concepts that would otherwise take hours of forum hunting on Stack Overflow.
And beyond just explaining concepts, Claude Code is exceptional at the scaffolding. When you are learning this language, you want to focus your absolute maximum mental energy on the core features: ownership, borrowing, traits.
Stuff that matters.
Right. You do not want to burn your cognitive budget figuring out the boilerplate of setting up a complex Cargo.toml, or configuring module directory structures, or writing the repetitive scaffolding for custom error types. Claude can generate that boilerplate instantly, so you can focus purely on the semantics of the language itself.
Which is vital because, as the text notes, the learning curve is almost entirely front-loaded. Those first few weeks are a grind, but there's a light at the end of the tunnel.
A very bright light. Once you grow ownership, once that specific mental model finally clicks in your head, the entire rest of the language falls perfectly into place.
That's reassuring.
Because everything in Rust builds on that one foundational system. Traits, error handling, asynchronous programming, concurrency. They are all meticulously designed around the rules of ownership. So every new concept you learn after those first few weeks requires less and less mental adjustment. It snowballs in your favor.
Okay, let's take a step back and look at the journey we've mapped out today. We've moved from the theory of Chapter 1 into the reality of Chapter 2. You've got the ultimate tool belt now. Rustup to manage your toolchain, Cargo to orchestrate literally everything about your project, from dependencies to optimized LLVM builds, and Clippy to act as your strict, idiom-enforcing mentor.
You also understand that the Rust ecosystem is built for the long haul. Cargo's deterministic lock files and the genius of additions ensure that you will never face an ecosystem-shattering migration. You can confidently build enterprise software knowing the foundation is rock solid.
And finally, you have a concrete strategy for surviving the brutal first month. By using Claude Code not as a crutch to write your code, but as a tutor to compress your feedback loop and translate alien concepts into your existing Python and Java mental models, you're going to flatten that learning curve significantly.
Which sets us up perfectly for where you are headed next in the series. Because now that your environment is pristine and you know how to leverage your AI tools, Chapter 3 is going to tackle the biggest paradigm shift of all.
The elephant in the room. Ownership and move semantics. It is arguably the most important topic in the entire book. After you conquer that, you'll get into borrowing and the borrow checker in Chapter 4, and how to actually model your data using structs and enums in Chapters 5 and 6.
It's a progression, but ownership is where Rust starts feeling genuinely unlike anything you have used before. It is the core innovation that makes the whole language possible.
It's going to be a fascinating shift in how you think about memory. But before you go fire up your terminal and install Rustup, I want you to think about your calendar last week. Think about how many hours you spent debugging a mismatched library version. Think about the time you lost fixing a broken Docker build because a sub-dependency updated overnight and broke your Python environment. If Cargo and Rust additions make all of that accidental complexity simply vanish, what are you actually going to build with all that return time? We'll see you in Chapter 3.